don't have to worry about voting for all the others. I've written it here as if you got a single value. Now that you have theta, you can solve your equation directly, just as we did before, and we increment our accumulator array. The nice thing is that by using the gradient, you've reduced the voting time hugely, right? You don't have to worry, you just have a single point. Also later you can use it to reduce the dimensionality. So this is the extension that people make use of the most. In fact, the whole notion of orientation is something we'll talk about more going forward. A few other extensions. One is, well, remember when we were doing edge detection, we said that some edges had stronger magnitude than others, and you have to set a threshold. Well, you might lower that threshold a bit to try to get more edges, but the idea is you might want to count the edges with a higher threshold more. Well, what would it mean to count them more? Well, you can imagine that stronger edges would get more votes. Another extension, and this is similar to what I was talking about before, is playing with or changing the bin size of theta and d. As we said before, big bins make it easy to, first of all, vote, it's fast, but you sometimes can get similar lines landing in the same bin. Too fine a bin, and you have this problem that the real line, because of noise, votes for different bins. So extension is to do this hierarchically. First, do a coarse binning where you have sort of larger bins that capture more values. Once you find peaks there, you then go to finer arrays just within those areas, and you improve your recovering of the model. And finally, it's not just an extension, but it's a whole new way of doing things. We did this for lines, but you can do this easily. I shouldn't say easily. You can do this pretty straightforwardly for other parameterized types of shapes, like circles, which in fact we will be doing in a little bit. Oh, and you'll be doing as well. Or actually any other shape, including shapes that are defined by their templates. So that's the end of this lesson. You will undoubtedly go back and look at this pretty carefully, since this algorithm and the manipulation of the data sets are going to serve as the basis of the first part of the Huff problem set. And when you look up this stuff on the web, which many of you will, you'll want to relate that back to what was seen here. And I'll tell you this, implementing the Huff transform feels relatively straightforward. That's why people, when it was on a course where the problem set was due Sunday night at 11:55 p.m., many of them started it around 6 p.m. They later reported that it took them more like 10 hours to do this problem set, and that's because the extensions, the circle setter, nothing quite works exactly like I say it does. That, by the way, is going to be a lesson of this class. The papers, first, what we say in class never works, because it's a distillation of the simple stuff. What we say in papers hardly ever works, because we have to make it very, sound great for publication. In reality, stuff works. You take the theory, and then you have to massage both the imagery and the algorithms. All right, welcome back to computer vision. So having done lines, and remember lines are sort of the easiest version of a parametric model, now let's move to something just a little bit more complicated, namely circles. So here's the equation of a circle. You remember this from Mrs. McGillicuddy's algebra class. X minus a squared plus y minus b squared equals r squared, where a and b are the center and r is the radius. And for now, we're going to assume the radius is known. How did you know it? Megan sent you a postcard and said the radius is 11. Okay, fine, so you know the radius. Oh, and we're also not going to use any gradient information just yet. We're just going to find the location of the points. So here we have a circle. We don't actually know where the circle is, but we've detected, say, 3 points on that circle, the blue dots here. Okay? So what is the Huff space? What is the accumulator array space for the circle? Well, since there are typically 3 unknowns, a, b, and r, but I told you we know the radius, Huff space is just a and b, right? The center locations in the x and y direction. So now let's consider the first point. So let's say x0, y0, this point right here, okay? So that point has to lie on the circle, and we know its radius. So one way of thinking about that is that the circle has got to be some radius r around that point, all right? And so what that does is it votes for a set of points. And that's what this green line represents, right? This set of points that are around this location in the AB space, okay? So for a single point in the image space, we get a circle of radius r in the Huff space, all right? Let's move to the next point. Well, same thing, right? So it's got to be, again, a radius r around here, and in Huff's space, we're going to vote along this circle. And again, the next point. And so if each point votes, each point in the image votes for a circle, we collect all the votes. And so just as before, we get the majority of our votes here, and that corresponds to this middle point, and that's what's drawn there. So it acts just like before, where we're voting for lines, except now instead of using the sinusoids, we're voting in a circle in an AB Huff space. And in fact, here's a nice little example of the thing running. And this is taken from a very ancient photo, but you can see right in here, there's a bowling ball, and that's where the crosshairs are drawn. And just as a sort of to show you some other way of trying to find this ball that's moving, you can imagine just looking for the stuff that's moving. After all, it hasn't hit the pins yet. But when you look for the stuff that's moving, they find this bounding box. How come we find more than just the ball? Well, actually, if you take a look really carefully, you'll see that this lane is very shiny. Okay? In fact, in a little while, we're going to talk about reflectance functions and specular reflectance functions, and you'll talk about why on this lane you actually see the image of the ball, and because of that, there's motion in here as well, so you get this bounding box. But that's okay. What we're saying is basically that it was able to find the circle. Here's another example taken, in fact, if you go and you type Huff transform circles or something like that into Google and look for images, you'll come up with this image. This image was actually taken by Vivek Quatra back when he was a wee graduate student TAing my class back in 1811 or something like that. And what we did was we took a picture of these coins on top of a textured background. He did it because he had to, because he was my TA. He's now really a famous guy doing cool research stuff. All right? So basically, you can take this and you can compute the edges, and then here's an edge image of that, and then we can look for circles. Now, we're going to use the known radius method. So let's suppose we start with the radius for a penny, all right? And you can probably see that there's this nice bright spot right here in the middle. That corresponds to the penny. Now, what you may also notice is that there are these kind of blown up areas, not so much here, it's a little harder to see. We'll go back here. And that's because you could fit a penny sort of around the edge of this circle, and the centers would be rotating around the middle of the circle, and that's what this little circle of centers is. But at the real penny, they all line up, and so you get even a brighter spot. So how would we find the quarters? Well, we just use a bigger radius, the radius of a quarter, and we vote again, and again you'll see these spots here, here, and here. And now the penny edges, well, they again vote for this bit of a circle, but not nearly as strong as the quarters do. So this was the original image, and these are the combined detections. And so that's pretty cool, you can just find the circles. But suppose you don't know the radius, okay? Megan sent the postcard to the wrong place. You moved because you wanted to upscale your apartment, and now you know you shouldn't have because you're left without a radius. So what do we do? Well, let's think about it this way, all right? Now our Huff space has 3 dimensions, A, B, and R, because we don't know what the radius is, all right? So now if I have a single point, what happens? Well, now, if we knew the radius, let's say the radius was, 7 over here, then it would be some sort of a circle centered about this point, right? Just like that we did before. And if the radius was, let's say, 3, it would be another circle centered about the same point, but smaller. So I hope you can start to see that what we're getting in here is actually a cone, okay? So with unknown radius, each point votes for an entire cone in this 3D space. So the surface of the cone, right? Not a filled-in cone, but the cone that's a surface. And the next point, what does it do? It votes for another cone. And you can sum these all up. Now, I will tell you, this is pretty painful. And in fact, if any of you end up doing a problem set for some random course like this one, we're going to tell you in terms of looking for circles, if you try to vote in a great big 3D space, it's not going to work so well, and in a whole bunch of lectures later when we teach you about ransack, it'll sort of overcome this dimensionality. But for now, just know that we have this little problem of growing the size of the voting space. So it can be done, it's just a little bit painful. But remember before, one of the ways we got rid of the number of votes you had to do was by using the gradient direction, okay? So, because like if I had a point and I knew the gradient, there was only one possible line it could be. Well, we can do the same thing with circles, all right? So now we have an unknown radius, but we have a gradient, all right? So again, our Hough space is A, B, and R, but this time our one point here has this gradient, okay? Well, now if we knew the radius, we would just have one possible circle it could be, right? So if you tell me that this is a point and that this is the gradient and I know the radius, that's the only place the center can be. But if the radius was half that, then the center would be there. Or the center, I guess it also could be on the other side. So there's just this single line of voting that can happen when you have the gradient, and that's drawn like that. So in the Hough space, even though it's a three-dimensional Hough space, you would only vote along one line. Okay? And so that's a little bit better. At least it makes the voting easier. You still have this problem when you have this three-dimensional Hough space. So here's the algorithm sort of simply described for circles. Just like before, for every edge pixel, for each possible radius, right? So we don't know the radius. And then either for every possible edge gradient, if we vote for the cone, or if we use the estimated gradient, then we compute A and B, and we increment for A, B, and R. All right? And then that would just vote you in your Hough space. In general, even though 3D is only 50% more D than 2D, you'll find that voting in 3D is way more than 50% harder than 2D. And that's because just one way of thinking about this is, let's suppose you had 100 buckets in each dimension. Okay? So how many would that be if you had one dimension, Megan?
100.
And if you had two?
10,000.
And what if you had three? All right? That's 1,000,000, right? 10 to the 6th. The number of cells that you have to consider is exponential in the number of dimensions. And that's a challenge with using the Hough transform. So a couple of practical tips with voting for the Hough transform. One thing you want to do is try to not do too many irrelevant votes. So try to minimize sort of edge elements that are not robust or highly unlikely to be useful. Because remember, we don't have to find all the points along a line, just enough of the points. You want to choose a good grid discretization for your Hough accumulator array, right? How many bins you make. And there's no sort of magic answer to that. It's a little bit of an art. The problem is if things are too large, the bins are too large, then too many sort of false points vote for the same bin. And if the thing is too fine, then a little bit of noise will cause you to vote for the wrong bin. So there's this trade-off. It's sort of how coarse and fine the data structure is. There are other things you can do. You can actually say, well, I'm going to take my point and I'm going to vote for the bin, but maybe I'll also vote for bins nearby, because maybe I'm not exactly where I need to be. It's a little bit like smoothing in the accumulator array. That actually can help. Using the gradient or the edge direction reduces the degrees of freedom of your voting by one, and sometimes that's very useful. And then the last thing is, once you've found, let's say, the circle or the line, you can go and draw it in the image. But if you actually wanted to find the edge points, well, you could do a couple of things. One is you could actually try to look along that circle looking for those edge points, or you could have been more clever to begin with. You could have, when you voted in those buckets, in those bins, you could have kept track of every point that voted for that bucket. And then once you have a winning bucket, you go and you look in that bucket, and there's the list of points that voted for it. And that way you could find the points in the edge image that actually selected that object. So some pros and cons of the Hough transform. All the points are processed independently, so it's okay if part of my stuff is occluded because each point just gets to vote. There's a modest amount of robustness with respect to noise. So because the noise points, as we said before, they're unlikely to sort of collude to vote for the wrong thing. And you can use it to find multiple instances of the object within the single image. There are some downsides. The biggest challenge is that the complexity goes up exponentially with the number of model parameters. So you're never going to use this if you've got like 7 model parameters, or maybe even 4 that you're trying to explore. You'll have to use other methods. And the other thing is, if you have sort of non-target shapes, suppose instead of circles you actually had slightly squashed ellipses, then the voting can break down, and you have to be careful in terms of how you handle that. And as we said before, the quantization, it is hard to pick a good grid size and does require experimentation. Look, that ends the lesson on using Hough transform to find circles. That, along with the lines, is sort of the sort of very old approach to a parameterized method, methods of finding parameterized objects. Even though it's old, it's a good way of learning about